Broadcasting from Studio 202 at the Springett Technology Center in Navasota, Texas. It's NOV Live. Now, here's your host, Michael Gaines.
Hello and welcome to NOV Live. I'm Michael Gaines and glad you're joining us today as we continue a conversation bringing you technologies and technical experts who are helping make a difference in the world of energy. And so today is no different in bringing you some really interesting technology. On this episode, we're going to be talking about mud cooling for high temperature drilling. And personally, I find it a really, really interesting technology and think that the application certainly has great impact in a broad space within the energy industry. So looking forward to bringing our guests in just one moment. Before we do, I'm going to head over to our social media desk with Shelby Dumaine to talk about how folks can be a part of some of the previous conversations we've had and, of course, today's conversation.
Absolutely. Thanks, Michael. Yeah, so if you're watching this today and would like to get involved in the show, the best thing you can do is by commenting any questions you have for our experts here in the comments. Whether you're watching this right now on Facebook, LinkedIn, or YouTube, we are live, so you can type in your question, and at the end of the show, we're actually going to do a live Q&A where we will answer as many questions as we can. And I always like to say, if you want to test out the comment section, if you want to let us know where you're viewing from, I love seeing where everybody's watching from. I get to see, all kinds of different folks from different countries and places in the world tuning in, so I'd love to see that. But in the meantime, between now and the end of the show, feel free to let us know any questions that you have as well. And as Michael mentioned, you can also check out past conversations we've had. All episodes of the show and our other show, Inside Out Horizons, can be found at nov.com/live. So you can go to that link, check out. I always say you can binge watch the shows if you'd like, or watch one every now and then. And if you have a question on any of those past episodes that are no longer live, you can email your questions to socialmedia@nov.com. And we'll make sure to get your question answered by those experts. We don't want any questions to go unheard, so we are here for you to answer your questions. And so those are all the ways you can get involved. Like I said, today, if you want to get involved live with this show, just comment below and we'll get those heard. But that's all the ways you can ask us your questions. Now it's the part of the show where I ask you my question. It's time for Rig Geek Post of the Week.
Rig Geek's Post of the Week.
And if this is your first time watching, this is a trivia question we like to ask here at the top of the show, and then at the end we will reveal the answer. So get your typing keyboard fingers ready to answer this. Today is a true or false question, so all you have to do is tell us if the statement is true or false. And the statement you'll be judging is: in below freezing conditions, drilling mud needs to be cooled. True or false? Go ahead and let us know below. You might maybe hear the answer throughout it, maybe not, but at the end of the show we will reveal that. So if you think you know the answer, go ahead and let us know. And with that, I will see you at the end for the live Q&A, and I'll be sure to see your comments in the comment section.
All right. Thanks, Shelby. Okay, so today we have the opportunity to actually have two experts with us. We have Mark Canlas, who's the technical sales, industrial products and services, and then we have Ian Holman, who's engineering manager for product design, and both of them are going to be joining us today to talk about, again, mud cooling for high temperature drilling and a specific solution called TundraMax. So Mark, Ian, thank you for joining us today.
For having us, Michael.
Glad to have you. Yeah. So, when you're thinking about drilling and really the space of drilling mud, of course, there are a lot of things that come to mind. But one of the things that may not necessarily immediately come to mind is the mud temperature, and specifically, making sure that it's at the proper temperature and cooling that down. So I know that with the TundraMax, that was the result of some a conversation, of course, with customers, but also finding an innovative way to solve that space. So maybe I'll start out. I know I've given a little definition, but Mark, can you kind of talk a little bit about Tundra Max and really what it is?
Yeah, no, sure. To really answer the question about what Tundra Max is and what it does, we kind of have to take a few steps back and start with industry as a whole. We're drilling faster, we're drilling deeper, we're doing things with our equipment tools that we've never been able to do before. So with those advancements, we find ourselves in some more complex drilling situations like HPHT, high pressure, high temperature, and geothermal drilling. So we continue to push those limits with faster ROP, longer laterals, and with that, as we go deeper, temperatures downhole are also increasing. They're getting hotter, and that combination of heat and frictional force becomes a perfect formula for overheated drilling fluid. So as the temperature of the mud goes up, you start to have other considerations that come into play. Other safety risks with people that may come in contact with the high temperature drilling fluid as it returns back to surface. You have surface equipment that's relied upon for safety and for functioning of the drilling operations. Those have components where reliability becomes an issue at higher temperatures, and that equipment starts to get taxed. And then the downhole tools, which oftentimes have complex sensors and electronics, when you're encountering higher than normal temperatures, you start to see failure. And it can start to deliver inaccurate data, which is obviously not what we're looking for. And then, specific to the drilling fluid, you start to see issues with stability and challenges in maintaining the desired fluid rheology. So I say all that so that we can kind of circle back to your original question. What is it? Our Tundra Max onshore mud chiller, as its name implies, is our solution to managing elevated drilling fluid temperatures. And we do that by actually cooling and chilling the drilling fluid at surface before it's sent back down. The Tundra Max unit was engineered specifically for land applications. It's self-contained. It's a single lift unit. It can arrive at the site on a trailer mounted and ready to go. So the rig up and the operation can happen quickly and in the same day. So our unit can treat water-based, oil-based, synthetic-based mud. And one of the values to Tundra Max is one of the limitations it overcomes compared to other conventional land mud cooling units is that it doesn't require an external water source to replenish water that's evaporated through the mud cooling process. So for other units, sometimes that means they've constantly got to bring in water or truck it in, or they've got to be located next to an external water source, which isn't always feasible. Our Tundra Max unit is a fully closed loop system. So the water it starts with essentially is the water that it ends with. So, and in remote areas, that can be a huge advantage. So I mentioned all these challenges and issues that you start to encounter when you're drilling mud temperatures that are starting to approach that threshold of high temperature. With our Tundra Max unit at the well site, we can essentially help mitigate and prevent those issues from becoming detrimental and unsafe. When it's running, it's reducing the temperature gradient while drilling. So your bottom hole temperatures start to decrease. You don't see the higher temperatures as fast or as early in your drilling program. You're lowering the mud temps at surface. And in turn, you're improving tool reliability, you're improving safety, you're extending the tool life, and you're able to maintain that desired fluid rheology for the duration of your entire drilling project.
No, that's a good overview. Thinking about the impact that it has on equipment and also the safety factor alone are two things that can be easy to miss. And so I think that's really good to bring up those points, along with ensuring that the overall efficiency of the program is maintained. So. So that's helpful, Mark. I did want to ask Ian. Of course, Mark gave us a high-level overview, and so at this point, I'm kind of curious to talk to more about really the overall way the system works and how we were able to accomplish the actual cooling of the drilling mud, because I know that's something that for folks like myself that are a little more technically minded, it's like, okay, great, I get the concept, but help maybe dive into a little bit more for me.
Sure. So as Mark kind of mentioned, the unit is easily transported and set up on site. And so it can be trailer mounted or rigged up, removed from the trailer and directly set on the well pad or something, wherever they have the room. And we actually tie the mud chiller directly into the active system. So what happens is you connect, once the mud chiller is actually on site, you connect to the active system. Typically, we take our feed into the chiller from the suction tank. This is the same tank that the rig will be supplying, or will be supplied the drilling fluid to the rig floor to eventually go down hole, and then it's returned back to the active system. And so we take the suction for the mud chiller from that suction tank because it's the coldest temperature in the active system of the drilling fluid. So it's already had some ambient cooling effect that's happened. So the temperature has already dropped down to a more stable temperature range. And we feed that into the chiller and then return and cool the drilling fluid down as much as the chiller is capable of doing, or to a target temperature. It's either just full blast, you can turn on and let it cool down as much as you can get it, or we can target a specific temperature that the drilling rig or the drilling operators might want to have. We return that temperature back into we return that drilling fluid back into the highest temperature zone of the active system, which is typically the drilling fluid that's being returned from the rig. What happens is we're dumping the coldest mud that we can get into the highest temperature range on the active system, and it generates kind of a heat sink in the active system. And that just helps us, one, get the most efficiency out of the chiller that we can, and then two, it helps maintain an active system temperature, which is more often what the drilling operators are looking for. They're looking for us to maintain like a target set point in that active system. And we do that with the chiller through, actually, it's a really interesting process. It's actually a patented process. It's a two-stage cooling process. Essentially, the drilling fluid is pumped into the mud chiller. It goes through a heat exchanger that has its own closed loop water system. That's the first stage of it. And that stage uses ambient cooling to take the initial kick out of the drilling fluid. Then it leaves that first heat exchanger and goes into the second stage heat exchanger that is tied to our chiller system. And so the chiller system actually uses an HVAC system to maintain the water loop. Both stage 1 and stage 2 do have independent closed loop water system. So as Mark mentioned, you don't have to feed this with water. You don't have to have a separate water source. The unit can arrive with water already in it, or you just pump some standard potable water into it, and then it just maintains that water loop in itself and the water volume in itself. So once it's supplied to site and you've hooked up power and you've hooked up into the active system, and that drilling fluid goes into that first stage, and again, it's dependent on ambient temperature. It works fairly similar to a radiator on your car or something. So the water will flow through the loop. It goes through some giant radiator coils, air cooling. It comes across the coils. It takes the heat out of the water and just transfers it into the ambient environment. And then that cooler water is then pumped into the heat exchanger. And the drilling fluid is entering the heat exchanger on one side, the water is entering on the other, and then the heat is just transferred from that drilling fluid into that water. And it's a continuous cycle. Then it goes back through those cooling coils, air is blown across it, removes the heat from the water, the cooler water enters the exchanger, and again takes the heat from the mud. That is the first stage. Like I said, that's initial little drop in there. The better the ambient, the lower the ambient conditions, the better the first stage works. The higher the ambient temperatures, the less efficient it works. And that's actually where we have a patent pending for the controls of that to knock off that stage 1 when it's not actually doing anything effective to the mud. So if the higher ambient temperature, if the ambient temperature is higher than the drilling fluid that's actually entering that stage, it will disengage that stage 1, and you won't be doing the reverse effect of heating the drilling fluid.
Right.
So that's really unique to us and to our unit with that first stage. And then for the second stage of it, that's the HVAC system. So again, the closed loop water system. The water flows through a chiller. It's basically a refrigeration system. It's a 150-ton rated unit. So it's got a massive amount of power that it can take, or a massive amount of energy that it can take out of that water, which is just heat. So it maintains that water temperature, and then that water temperature, same effect. It enters into the heat exchanger with the drilling fluid. So the drilling fluid enters on one side of it. The water enters onto the other side of it. The water takes the heat out of the mud and then flows back into that chiller system. Whereas with the stage 1, it's just using ambient airflow to cool the water. It's using a chiller system. So it's using a refrigeration system to drop that water temperature down to a target set point. We can actually achieve a water temperature of 40 degrees in that water loop. So you can actually pump 40-degree water into the heat exchanger on the opposite side of that drilling fluid. And that's where the most temperature drop occurs. So that first stage kind of takes that initial, anywhere from, a few degrees to several, 10 or 15 degrees. And then that second stage takes that final kick. And that's where we're able to maintain that mud temperature. Whereas instead of being dependent on just ambient conditions, like with a simple air blast unit, you can use the chiller system and that controlled water loop to control the drilling fluid temperature that's coming out of the unit.
I know that just seeing and not only hearing your walkthrough, but also seeing some of the diagrams or flow diagrams helped me understand a little more about this technology. I've known about the TundraMax for a little bit, but I don't know that I was able to really grasp the really some of the process flows, and so that's helpful. Answered a couple of my questions. I know that as always we have folks that are watching that probably have their own questions. So if you're watching on LinkedIn, YouTube, or Facebook and have been listening to our conversation about the TundraMax mud chiller system and have a question for Mark or Ian, feel free to put that into the comment section wherever you're watching us, and we'll try to get to as many of those questions as we can before we wrap up the show. I know that we already have some questions that are coming in, so feel free to put those in, and then we'll get to the Q&A portion in just one moment. So before we do, Ian, I want to stick with you and maybe talk about some of the experience that we've seen with the TundraMax, but specifically talk about some of the experience that our customers have had, and maybe any case studies or kind of field-based experience you can share with us.
Sure. Yeah. So we deployed the unit in actually a trial situation in South Texas. We were working in the Eagle Ford formation, and we wanted to see the direct effect of a mud chiller when it's deployed on a rig and when it's not deployed on a rig, and very similar drilling programs and very similar formations, and we even using the same rig to make sure that the same operators, everything, so we can again remove as many of the variables to see how much the mud chiller affected the drilling operation. And so again, we were in South Texas. It was the Eagle Ford formation, one rig, and they did 2 wells back to back. And in the first well, they did not deploy the mud chiller at any time during the operation. And then the second well, they deployed the mud chiller during the high temperature zone, because the focus was primarily how the mud chiller affected the drilling operation during that high temperature zone. Most of those high temperature zones end up being past the 15,000 feet. Usually it's the last, 3, 4, 5,000 feet that they're trying to get to when they get to that 18 to 20,000 depth. And so what we saw was a drop. Well, one of the most significant things that we saw the drop was the temperature gradient. So the temperature gradient is the expected rise that you should see as you go deeper and deeper during the drilling process. And so what we saw was a reduction in that gradient by about 20%. We've actually seen it higher than that in some other instances. But by dropping that temperature gradient, or that expected rise that they were seeing as they were drilling further, just prevented the rapid rise in that downhole temperatures. And preventing that rapid rise in the high temperatures, helped improve tooling life and everything else downhole, and then also helped with mud rheology and everything, as Mark mentioned before. The other big thing that we saw was just the reduction in the bottom hole temperature during that process because of the reduction in the temperature gradient. So the natural energy that was occurring during the drilling process was not being affected as much by the temperature rise or the temperature gradient that they were seeing. Another key thing that we saw during this was the comparison and the amount of time that they were having to drill through those high temperature zones. So whenever they're in these high temperature zones, a lot of times they'll do recirculation. So they'll either completely stop drilling or drastically slow down the drilling process with the attempt of circulating fluid at the surface, getting it cooler, and then lowering the temperature downhole. Whenever the mud chiller was not in use or not being utilized during these high temperature zones on that well previous, it took them 125 hours to get through that high temperature zone to get to the final depth. Whenever they deployed the mud chiller on the well after that, it actually reduced it down to 75 hours. Oh, wow. So they actually reduced the drilling time during that high temperature zone by 2 days. And one of the key things that happened with that is the amount of time that they were having to recirculate was less. So rather than taking 8 hours or 10 hours or 12 hours to circulate to drop the bottom hole temperature, they were only having to circulate for 2 or 3 hours. That also increased their rate of penetration during that high temperature zone. So on the previous well, when they were in that high temperature zone, they were only, the rate of penetration was only 30 feet per hour. Whereas on the second well, with the utilization of the mud chiller, they were actually able to get 60 feet per hour during the rate of penetration. So it just sped up how much they were able to drill, and consequently reduced the drilling time.
Right. Yeah, and I know. So that and that's a really interesting case study to really see that. I know, Mark, I think you had a similar or another case study as well that talked to some of the performances that the Tundra Mac was able to achieve in the field as well.
Yeah, no, as Ian described in that case, our job is to lower the mud temperature, but ultimately our customers' end goal is really about reducing or eliminating NPT, non-productive time. When their equipment, especially their downhole tools, when they're not reliable or they're not functioning, and they have to shut the rig down, that becomes a huge issue. So in a case where we utilize Tundra Max, there's a customer who was drilling a series of wells, and they were utilizing some downhole dynamic measurement tools. As they were, so on one rig where they were not using Tundra Max, and they were drilling, and the bottom hole temperatures started to increase and exceed the functional threshold of their measurement tools, they began to fail. So this tool had a maximum battery life of 250 hours. In the case of the rig without any mud cooling or mud chilling, the most they were able to achieve was 167 hours of operation, which is 67% of that battery's capacity. Now, this was an environment where the bottom hole temperatures started to exceed 300 degrees Fahrenheit. So in the same area, same client, they drilled a separate well. And in this instance, we activated and we ran the Tundra Max. They were able to drop the bottom hole temperature. And in this case, that dynamics measurement tool was able to gain 240 hours of its max capacity of the battery. So that was 96% of its total capacity. So between the two wells, one without Tundra Max and one with, we were able to increase that dynamic tool's battery life of 44%. This in turn reduced the need or the number of trips required. So their overall drilling rate was better. They were able to actually drill that well 3 days faster than the previous without Tundra Max. So
Right.
Again, I had mentioned tool life, tool reliability, and this is a case where our Tundra Max and being able to control the downhole temperatures contributed to that.
So it's really interesting to see where this technology has been able to come and obviously work in the field. Curious to know, kind of where we are today if we're looking at some of the advancements that we've been able to make as a team. I know that both of you and many others between Mark and Ian have worked hard to make sure that this is a technology that's really helping our customers. So where are we at today with Tundra Max?
Yeah, so we've actually got several of these units already deployed, and they're deployed in different regions. Primarily, I think that most of them are being utilized in the Middle East. But as far as where we're going with the next phases of this, we're looking at implementing the NOV Max platform into the mud chiller units. So then NOV Max platform was developed by NOV when it comes to kind of our solution to big data. And so we've been trying to find a way to incorporate some of the aspects that the Tundra Max take advantage of, which is the automated cooling that we have the patent pending on and stuff like that, but then relay this information to the operators and the customers. So with the Max platform, we're able to do that. And by incorporating with a Max Edge device into the control panels, we're going to be able to provide remote monitoring and remote capabilities for the operators and the customers. This will also allow us to be able to share data across units and across operators and across different regions. And with this edge device, just with a simple cell signal or tie into a network through an Ethernet cable, we're able to get and provide that remote access. It just gives a better tool for the operators. It also allows us to start tracking better trend history and performance data of the units to see how they're affecting the drilling operations, give better reports, and just prove to the customers and the operators how much we're providing for them with the use of the mud chiller. This also allows customers to be able to access the information in real time. So they'll be able to get mud in, mud out temperatures, how much power consumption is coming from the unit, and be able to incorporate that into their reports and their performance of their drilling operations. With the Max platform, we'll also be able to incorporate a maintenance program. So it'll be an automated maintenance program to give notifications of when maintenance needs to happen, any upcoming maintenance, planned downtime for the unit, and then also potentially have the option to target when something might be going on with the unit so that we can troubleshoot it faster, to just maintain that 100% utilization of the chiller on site.
Mm. Well, I think this is I mean, at the base level, the concept is, to me, really innovative and really makes sense when you're looking at the problem statement that it's able to solve. As always, I have far more questions than I probably should ask, and so for that reason, I'm going to make sure that I get out of the way so we can get the questions from viewers, because that's really what they want. So Shelby, I know that you've been typing away over there. What questions do we have from folks?
Yeah, we have some excellent questions already, and you still have a little bit of time if you want to try to get a question in. But this first one comes from Jack on LinkedIn, And he was wondering, does this work with both oil-based mud and water-based mud? And in oil-based mud specifically, does water content at all affect coolability?
Yeah, so the unit can be used in any drilling fluid-based material, water-based, oil-based, synthetic. We can even use it in brine conditions if needed. And as far as the water percentage, the oil-water ratio in the drilling fluid, it doesn't really play that much of effect in it. There's a different trend in between water and oil-based just because of the thermal properties that are associated between water and the oil-based. And a higher content water in the oil base will affect that thermal conductivity a little bit. It'll improve it slightly, but there's not really that much of a drastic difference between the two conditions since we are using water as a cooling medium as well.
Mm-hmm. Yeah, thank you. This next one also comes from LinkedIn and is asking about the effects of recycled solids in active systems like erosion or plugs to lines. Do the mud chillers at all play a part in that and mitigating those effects?
As far as mitigating the solids and stuff and affecting the active system, no. It doesn't really have any effect on any of the solids effect on the active system side of it. We are limited in just kind of what the amount of solids that you want to put through the chiller because any kind of solids do provide the potential of plugging it. That's one of the reasons that we also take our suction from the suction tank because it is the cleanest mud in the active system. So, and any kind of solids content in the drilling fluid will affect the cooling rate and the cooling capacity. But overall, it doesn't make that big of a difference in the sense of the performance of it. It just helps prevent from any kind of plugging that might occur in the heat exchangers or something.
Mm-hmm. Thank you. And this next one comes from John on LinkedIn, and he was asking about the ESG score and carbon footprint. And I know something kind of in that space of lower carbon solutions that we've talked about on the show a lot is geothermal energy and that kind of space. Again, do the mud chillers kind of play a part in that space?
Well, I won't be able to answer. You mentioned ESG score, but as far as being involved in geothermal, we're quite active from that standpoint. We're seeing higher temperatures than downhole what we're maybe used to in traditional drilling. So we've been approached and we've looked at different setups and solutions utilizing multiple units. So geothermal is absolutely a category of application that the Tundra Max can function in and provide value.
Excellent. I appreciate that. And I think that's all the questions that we have time for today. But again, like I mentioned, if you still have a question that you'd like an answer to, go ahead and type it, and we'll try to have somebody either in the comments there answering it or reaching out to you to get your question answered. But I do want to go ahead before I hand it back over to Michael. I want to go over the Rig Geek question. So if you remember at the beginning of the show, I asked you, it was a true or false. There it is on the screen. We asked, in below freezing conditions, drilling mud needs to be cooled, true or false? And I think we had a little bit of a clue to the answer in one of the pictures that we showed of the Tundra Max, where it was, it looked like it was in the tundra. And so the answer to that, of course, is true. So drilling mud does need to still be cooled to prevent thermofrost. I think I said that right. Did I say that right, guys? Did I explain the true there? Correct.
It helps maintain the permafrost.
There we go. Maintain it.
There it is.
I knew I was gonna get it a little off, so I appreciate that.
Great. All right.
Yeah, thank you.
Well, thanks, Shelby, and certainly appreciate the conversation, insight, and from our experts again, Mark Canlas and Ian Holman, talking about the Tundra Max mud chiller system. So appreciate you both joining us, and as always, appreciate our viewers joining us as well. If you have a desire to jump into this conversation or look at previous episodes, feel free to head over to our website, nov.com/live. If you'd like more information on Tundra Max, feel free to head over to nov.com And in the upper portion of the screen, hit the search bar and type in TundraMax, and you can find more information there as well as get connected with us. So from all of us here at NOV, thanks for watching and for listening, and we'll talk to you again next time.
Thanks, Michael. Shelby.
Thank you, Michael.